Okay, let's get started. So we are going to look at section 6.2 today. This section is called integration of rational functions by partial fractions. As I told you from the last class that this technique, we got an idea from the partial fraction decomposition. So when you have, let's say you have x plus 5 over x squared plus x minus 2 here. So we gonna decompose this rational function into the smaller terms. So for this question, we can decompose x plus 5 over x squared plus x minus 2 into 2 over x minus 1 and 1 over x plus 2 here. So we can integrate easily. So one thing you have to keep in mind for this section is if we ask you to integrate 1 over x minus a dx, so this is easy. You can say this is going to be just log absolute x minus a plus c, right? Well, you can just pick your u to be x minus a, right? And by the chain rule, this is just dx minus a over 1. So it's going to be just integrate 1 over u du. So this is going to be just log x minus a. You're going to use this thing a lot. So keep in mind that this is very important. Another one is you're going to see integrate something like x squared plus 1 dx. For example, well, this thing is going to be just arc tan x plus c. This is by the formula of integration that we learned before midterm. We know that diff arctan, this is 1 over x squared plus 1. So when we have integrate 1 over x squared plus 1 dx, you get back to arctan. What if, well, let's do a review here because we're going to use this thing a lot today. So what if you see integrate 1 over x squared plus a squared? For example, you see 1 over x squared plus 16. How could you do this thing? So the idea is you're trying to factor out a squared first. So you're going to have integrate 1 over, well, I'm going to factor out a squared. So this is going to be 1 over a squared here. And then I factor out. So I'm going to have integrate 1 over here. I have x squared over a squared plus 1, right? So I factor out a squared dx. And then you can simplify a little bit. So this is going to be 1 over a squared integrate 1 over x over a squared plus 1. And this is going to come back to integrate of arctan thing. So you can just change the x now to the x over a, which you're going to get 1 over a here as a u substitution. So at the end, you're going to just get a over a squared times arctan x over a plus c. Well, if you simplify a over 1 over a over a squared, so you're going to get 1 over a, right? So this is actually going to be your tools that you're going to use a lot in this chapter. Well, we're going to do this thing a lot when we do the examples. All right, I hope you are ready, everyone. So we are going to talk about the theory of partial decomposition now. All right, take a deep breath. So we are going to look at the theory for a few more minutes, and then we're going to look at examples. So let's suppose that you have a function f, right? And then your function f is a rational function. So you can say f equal to px over qx. Well, your px and qx, they are both polynomials. So first of all, you have to make sure that your rational function is improper. The one that I highlight in yellow. By this, I mean improper mean the degree of p. Sorry. You have to make sure that the rational function is proper. So let's define improper and proper first. So improper means, so if you have improper rational function, this means degree of p, this is greater than or equal to degree of q. Well, by saying improper, this means you can reduce it into the proper one. So you can do the long division. If you apply the long division, so the improper rational function gonna reduce to proper rational function. So you can see that if you have px over qx, this is your improper rational function. If you do the long division, you can break it to sx plus rx over qx, where rx gonna have the degree of r that is less than q. For example, let's look at this example. So if I ask you to integrate x cubed plus x over x minus 1 here, before you use the partial fraction technique, so you can see that on the numerator you have the polynomial of degree 3. And on the numerator you have the polynomial of degree 1. Before you use the partial fraction technique, you need to make sure that the degree on the top is less than the degree on the bottom, which means I can do the long division. So you can do the long division here. So you're gonna do, hey, I have x cubed plus x and then divided by x minus 1. So you get x squared plus x plus 2, and remainder is going to be just 2. So by this, I have, hey, if I have x cubed plus x and my divisor is x minus 1, my result going to be x squared plus x plus 2, right? And then my remainder is going to be just 2. Well, which means if I have x cubed plus x over x minus 1, well, I am going to have x squared plus x plus 2, and then plus 2 over x minus 1. Well, that means I can decompose this thing that I circle it to something like that. So this is going to be the way we reduce the just use the long division to reduce the improper rational function to the proper one. So you can see that if I do that, so I can integrate the thing that I circle in red easily, and then I can integrate 2 over x minus 1 easily. Does it make sense? Well, before you use the partial fraction technique, just make sure you have proper rational function. All right. So now let's talk about how you set up the partial decomposition. So we're gonna tell you how to set up this thing. So if you have a linear factor x minus r to the m, so what you should do is you're gonna have the decomposition on the right hand side to be just some constant over x minus r, and then plus some constant over x minus r squared, and then some constant over x minus r cubed, and you keep going until you get some constant over x minus r to the m. Well, for each linear factor that I highlight in light blue here, you're gonna have m terms on the right hand side. This is how we decompose it. Well, similar to irreducible quadratic factor. So for example, if you factor out the denominator and at the end you get ax squared plus bx plus c to the m, and you cannot reduce more. Well, you already get this up to this thing, and then you are sure that you cannot reduce ax squared plus bx plus c anymore. So it means this is irreducible. So you can set up the decomposition to be, okay, the first one I'm going to have ax squared plus bx plus c here. And then I am going to have something on the top. Well, this is not just constant because on the denominator, I have ax squared plus bx plus c, which is degree 2. So on the top, I need to have something degree 1. So this is going to be a1x plus b1. And then plus, well, here I have ax squared plus bx plus c. So this is going to be a2x plus b2. Well, square here too as well. So plus, well, this is ax squared plus bx plus c cube. And then here on the top, I'm going to have a3x plus b3 plus dot 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 up to, well, if you have m terms, it's going to be amx plus bm over ax squared plus bx plus c to the m. So the idea is, first of all, you need to know how to do the decomposition. Once you do the decomposition correctly, everything is easy because you can just integrate the right hand side. Well, I'm going to show you some example that we wrote the example here. This is how we do the decomposition. So let's say I have 1 over x minus 1 over x plus 4 here. So you can see that on the denominator, I have x plus 1 and x plus 4. Both of these are just linear factor. So for x minus 1 here, I'm going to say this is a over x minus 1. And then for x plus 4 here, I'm going to have b over x plus 4. Does it make sense? Well, next, if I look at the second one, I have x squared plus 1 and x squared plus 4 here. Then because I have x squared plus 1 here, and I know that x squared plus 1 is irreducible. How do I know that x squared plus 1 is irreducible? Because, well, you can check by looking at the, well, if you have ax squared plus bx plus c, right? Well, your solution, the root here going to be negative b plus plus minus square root b squared minus 4ac over 2a. And then this going to have real roots when b squared minus 4ac greater than or equal to 0, right? If your b squared minus 4ac or discriminant less than 0, that's mean the root going to be complex number, and that's mean x squared plus 1 is irreducible. So you can see for this question, you have b equal to 0, 4, and then a equal to 1, c equal to 1. So this is just negative 4, less than 0. So the root of this polynomial x squared plus 1 is complex root. So that means this is irreducible. So you cannot reduce x squared plus 1 to a linear factor with real roots. So you have to stay with x squared plus 1 here. And then when you do the decomposition, this term gonna give you ax plus b x squared plus 1. And this term gonna give you another term here, cx plus d over x squared plus 4. Does it make sense? Well, the next one, you can see here, I have x plus 1 and x plus 2 squared here. So I'm gonna make the decomposition to be x plus 1 here, correspond to the factor x plus 1 there. Because I have x plus 2 two times, so I'm gonna have 2 terms here. And when you set up the constant on the top, you're gonna just, if the denominator is just the linear factor, you just put the constant. If the denominator is just this irreducible quadratic factor, you just put, ax plus b. Well, the last one, if you look at x minus 1 square here and x square plus 1 square, so you're gonna have x minus 1 square, x square plus 1, and x square plus 1 square here. Well, this is all theory about this technique. So, well, we can look at some examples now. Well, any question before we get into some examples? Well, I I will tell you that this technique is the easiest one in this chapter. So we're gonna learn 4 techniques, but for partial fraction, this is super straightforward. If you know how to do the partial decomposition, partial fraction decomposition, this is super easy. And when you just open the final exam, you can try to look for the question of partial decomposition. The idea is easy because you can see that if the question gives you integrate something in terms of rational function, that could be a partial fraction. And if you see that you can factor out the denominator, for sure, this is going to be the question about partial fraction. All right. Last time we just learned how to find some constants. You can, once you set up the partial decomposition, you can find the constant by using 2 ways. So compare coefficient or find the appropriate number. And then after that, we will have done example 150. I show you how to do the basic partial fraction. We're going to go to a little bit more complicated example today, starting from example 151. All right, so let's do it. So I have a question in the chat. Pimapon asks us that, do we have to show the solution for finding A, B, and C? The answer is yes. You have to show all the steps. You cannot skip some step. Well, if you skip it, I do not guarantee that you're going to get full credit. Well, this question, well, this topic, I told you, this is the easy one. So you should show your full work to make sure that you get full credit. Well, let's look at my solution here. And if you show your work, at least compared to me, you just show the minimum compared to me. It's like what I am going to show you. This is a minimum requirement to show your work. So if you show like I show in class here, so for sure you're going to get full credit. You cannot skip some step here. All right, so let's do example 151. So I'm going to start by, well, before you start doing partial fraction, make sure this is a proper uh, rational function. Well, you can see that the highest degree on the top is 2. The highest degree on the bottom is, this is degree 1, this is degree 2. So on the denominator, you have degree 3. You have degree 2 on the top. So this is actually proper. Good. I don't have to do anything. If this is improper, you have to do long division first. Well, now I'm going to make the decomposition. So for x squared plus 10x minus 30 over x minus 1 times x squared minus 9. So the decomposition going to be, well, before that, I factor out first. You can see that even I have x squared minus 9 here, or I have to factor out as much as possible first. So I'm going to factor this thing to be x minus 3 times x plus 3. If you still can factor, you need to factor until you cannot factor any further. Does it make sense? And then I'm going to set up the right hand side to be a over x minus 1 plus b over x minus 3 and plus c over x plus 3. Right? Because I have linear factor, linear factor, linear factor. So, well, the top going to be just constant ABC. Sounds good? So here, when you solve for constant, so let's look at my technique. So I'm going to just try to find the common denominator first. All right. So once I find the common denominator, so I'm going to just do a times, well, I have x minus 3 and x plus 3 here, right? And then I have plus b, x minus 1, x plus 3, and then c, x minus 1, x plus 3, x minus 3. All right, so I am trying to just find the common denominator, and I multiply everything back on the top. So now you know that the thing that I highlight in yellow here, the numerator, this is equal to each other. So from here you have 4x square plus 10x minus 30 equal to a times x minus 3, x plus 3 plus b times x minus 1, x plus 3 plus c minus 1, x minus 3. So from here, you need to solve for a, b, c. Well, the trick is here. You don't have to use the comparing the coefficient method. Why is that? Because you can see that if you expand everything, if you try to expand everything and then compare coefficient, this is going to be terrible, right? Because it's just tedious. It is not hard, but it's just tedious because you just need to expand and then compare coefficient. Well, I'm trying to avoid that thing, so I'm going to use a second method to solve a, b, c. So what are we going to do is, well, this is true for our x. Well, then we are going to pick some number and then just plug in into there so I can solve for a, b, c. So you can observe that if I plug in x equal to 1, what happened? If I plug in x equal to 1, then on the left, I'm going to have 4 1 square plus 10 times 1 minus 30. On the right hand side, I have a time, I plug in 1 there, so I get negative 2 and 4, right? And then here, once I plug in 1, so this term, 1 minus 1 is 0, so the whole thing here going to be 0. If I plug in 1 here, the whole thing going to be 0, right? So good. Well, that make my computation a lot easier. So I can compute here to be on the left, I have 4 plus 10 minus 30, which is negative 16, equal to negative 8 times a. So I have a equal to 2. Sounds good. So the next one, I can pick another number that's going to make my equation a lot easier because I see that I have x minus 3 here. I also have x minus 3 here. Wow. To solve b, so I'm going to plug in x equal to 3. So I have 4 times 3 square minus 10 times 3 minus 30 equal to 8. Wow, that term is 0. Sweet. And then this is going to be b times 2 times 6 and then plus 0. Well, on the left, I just compute that thing. 9 times 4 is 36. And then minus 30 plus 30, so that's 36. On the right hand side, you have 12b. Well, b equal to 3. Does it make sense? Well, pretty simple. So the last one, if you want to solve for c, for sure, I need to plug in negative 3. Because if I plug in negative 3, so what I'm going to have is that, and then that, and then that, and then, well, the a term going to be 0. The term equipped with b going to be 0 as well because I have x plus 3 there. And then the last one, I'm going to have c multiply negative 4, negative 6. Well, on the left, this is going to be a big number then. 36. Well, I need more time. So 36 minus 30 minus 30 equal to, that is 24c. Right? And that is what number? Minus 24 equal to 24c. So c equal to negative 1. You can see that this is pretty simple compared to you expand it and then compare coefficient, because you're going to have 3 equations and then you have to solve a, b, c from 3 equations. Well, pick the one you want, but usually I like the second way better because the second way is a lot easier in my opinion. But up to you. If you want to compare coefficient and solve, that's fine. Well, but keep in mind that once you do more decomposition, more and more and more and more, so compare coefficient is going to be the hard one because you're going to have more equation and then you have to solve it simultaneously, right? All right, so once you have that, so I'm going to copy this. Well, this is what I want to integrate. All right, we already solved something. So we're going to move this thing a little bit here. So the question that we have is integrate 4x squared plus 10x minus 30 over x minus 1 x squared minus 9 dx. Well, we already do the decomposition. This is going to be integrate that dx, right? And we already solved for a, b, and c. Well, a is 2, b is 3, c is minus 1. Well, that is 2 times log absolute x minus 1 plus 3 times log absolute x minus 3 minus log absolute x plus 3 plus c. Pretty simple, right? This is your solution. Sounds good. All right, so we're going to look at the chat now. So we have to show how to solve the simultaneous equation. So, well, from Pimapon question, so I just answered that, well, you need to show how to solve A, B, C. Yes, you need to. Well, but pick the method you want. If we sub, but all the terms do not cancel, so we still have to compare term, right? Yeah, so for this technique, well, it's going to be, you know, it's going to be your experience that you have to pick your x values that you can cancel out a, b, c. Sometimes you pick the values and a, b, c, they do not cancel. So that means you have to solve for a, b, c from what you have left. Yes, Serapop, you have to solve a, b, c from what you have left if you pick the wrong one. Suppose I don't know anything, I pick x equal to 0, x equal to 2. Well, that will not help me, but I can start solving for A, B, C from there anyway. All right. Thank you for those questions, you two, Sirapop and Pimapon. Those are good questions. So anything else? I think we have 2 more examples on this technique, and then we're going to move to trigonometric integrals. All right, not yet? Well, feel free to leave the question in the chat anytime if you want. So I'm trying to look at the chat from time to time. All right, so let's do example 152. I think, yeah, we have 2 more. So as I told you, this technique is the easiest one in this chapter. So if you feel like, hey, integrate, it's not my thing, at least you should be able to complete the partial fraction, because this is the simple one for this chapter. All right, by part is a lot harder. Trigonometric integral and trig sub is a lot harder compared to this technique. All right, so for this this question, you can see that we have the denominator here. Well, this is already good for setting up the decomposition. So we're gonna set up the 2x squared plus 3 over x times x minus 1 squared to be just a over x plus b over x minus 1 plus c over x minus 1 squared. Because you have x minus 1 squared here, so that means you need to duplicate the x minus 1 here 2 times. Well, that is the rule of decomposition. If you have x minus 1 to the m, so you're going to have m copies of x minus 1 with different power on the right hand side. Here, well, we are going to solve for a, b, c first, and then we can, just integrate it easily. So the denominator is going to be x over x minus 1 square. Well, this is going to be the first time that you see the denominator with square. So your a here gonna be x minus 1 square, right? A times x minus 1 square plus b times x minus 1 and c times x, right? Just that, right? Because we just make the common denominator now. So we have the top, the yellow one equal to each other. So here, what you have is 2x squared plus 3 equal to a times x minus 1 square plus b times x minus 1 plus c times x. Now, in order to solve for a, b, and c, so what should we do? So first of all, this is true for all x. You can pick any number x. You just pick it, and then hopefully you can solve for a, b, and c. The first one that I'm gonna pick is, you can see that I have x here. I also have x here. Well, let's pick x equal to 0. All right, we're gonna pick x equal to 0. So on the left I have 3. On the right I have a times 0 minus 1 square, and then 0, 0. Perfect. A equal to 3. All right. Another one. What should I do? Let's say I have x minus 1 here. Right. I also have x minus 1 here that I highlight in light blue. Let's pick x equal to 1. So because I hope that this two term gonna go to 0. And then 1 is go to 0. This is gonna be 0 plus 0 plus c times 1. That means c equal to 5. All right. What about b? Well, you can see that you can pick any x number, but well, if you pick any number, a and c will not cancel out. However, you already know the value of a and c. So let me do this. So I'm gonna pick b to be, let's say x equal to 2. Actually, you can pick any number. Let's say I pick b equal to 2. So I'm gonna x equal to 2. So you have 2 square plus 3 equal to, well, a times 2 minus 1 square plus b times 2 minus 1, and then plus c times 2. Well, you pick everything, x equal to 2. This is what you have, which means this is a plus 2b plus 2c. This is going to be, on the left hand side is 11, right? 8 plus 3 is 11. Well, that means 11 equal to a equal to 5, a equal to 3. B is the one you want to solve. C is 10. C is 5, so 2 times 5 is 10. Well, this is going to be 2b equal to negative 2, right? Which is going to be b equal to negative 1. Sounds good? Well, you can see that the last x that I picked, I just picked the random one, so I can solve for b. Well, if you want to show your power, maybe, well, I'm going to show that I'm expert in calculation. You want to pick x equal to 2020, whatever you want. Well, you can pick x equal to 2020. You can solve for b anyway, right? If you pick x to be 2020, you're going to get 2 times 2020 square plus 3 equal to, yeah, and then you just solve this equation. A times 2020 minus 1 square and whatever, which is going to be stupid because you just pick the big number, right? So you should just make your life a lot easier by just picking the small one. Well, as I told you, you do not need to pick x equal to 2. Negative 1 works. Any number works. Whatever you want. All right. I already got a, b, and c. So now we need to integrate this thing. Well, I'm going to copy everything here. Any questions so far in the chat, please? Anything else? All right. I have this. Integrate dx, right? So I'm so lazy, so I copy everything. Dx equal to integrate that. All right, and I already solved for a, b, and c. So from the previous slide, so my a gonna be number 3, my b gonna be negative 1, my c gonna be 5. All right, let's integrate this thing. Well, integrate 3 over x. Well, okay. Let's do this. 3 integrate 1 over x dx minus integrate 1 over x minus 1 dx plus 5 integrate 1 over x minus 1 square dx. All right, the first one going to be 3 times log absolute x. The second one going to be log absolute x minus 1. The last one going to be minus, too fast. So I'm going to just show you here that I'm going to switch the x to d x minus 1, right? The same thing. and then I integrate here. That means I integrate x minus 1 square, x minus 1 to the negative 2. So I'm going to get x minus 1 to the negative 1 over minus 1. All right, I'm trying to go slow. So negative 1 over minus 1, right? That is how I integrate it. And then plus c. All right, if I simplify a little bit, so this is going to be 3 times log absolute x minus log absolute x minus 1, and then minus 5 over x minus 1 plus c. All right, this is my final answer. Easy, right? Pretty simple and easy. All right. Sounds good. Any questions? Anything else? All right. Nothing yet. All right, good. All right, the last one for this topic. Well, 153. So let's look at the one when you have the quadratic terms in the denominator. Well, for example, here, well, I'm going to set up the decomposition first. Again, before you set up the decomposition, make sure you have proper proper rational function. Let's say I have x to the raised to the power 20 here. So that means you have to do long division first. So you get the, the term that you have the degree on the top less than degree on in the bottom. Well, here I have degree 2 on the top, degree 3 at the bottom. So that's already good. So I'm going to set up that. All right, x cubed minus plus 4x. Well, let's factor that first. This is going to be x times x squared plus 4. Well, when you see x squared plus some constant, I should say x squared plus positive constant here, for sure this is going to be irreducible because this term is always positive, right? And then when you match with when you compute discriminant, so it's going to be negative. That means this x squared plus positive number do not have the real root. So that means you're gonna have the complex roots, which means this one cannot reduce anymore. So this is the best one you can do about this term. So what you can do is you're gonna set up the decomposition to be a over x plus bx plus c over x squared plus 4. Well, if your denominator is x squared plus 4 like that, what you need is you need the top to be a linear factor, a linear term here. You need to have the top which 1 degree less than the bottom. All right, but the concept is the same. Once you set up the decomposition here, you can just clear out the denominator. So here I'm gonna have a times x squared plus 4 plus bx plus c times x. All right, I'm gonna simplify. Oh, I do not need to simplify because, well, I have 2x squared minus x plus 4 equal to a times x squared plus 4 plus bx plus c x here. All right, so you have two ways to do it. So you can pick any x number and solve for a, b, c, or you can pick, you can compare coefficient. So for this question, I'm going to show you how to do the comparing coefficient technique. I will do both way actually. So let's practice compare coefficient. So I'm gonna expand it. This is not terrible when you expand it. So you expand it, you get that, and that, and that. If you expand it, so you're gonna get a plus b x squared, and then plus cx plus 4a. So if you compare coefficient here, a plus b equal to 2. And here, -1. This must be the same with c. All right, c equal to -1. Right, and the last one you can figure out 4 here must be the same thing with this, which means 4a equal to 4. Well, here you get a equal to 1, c equal to -1, yes, and b must be 1 because a equal to 1. So you already get a equal to 1, b equal to 1, c equal to -1. Done. Well, this is called comparing coefficient. Sometimes it is easy, like this question, comparing coefficient is easy, right? But if you see that you have so many terms, like 4 terms on the right hand side, for example, comparing coefficient is going to be tough because you have so many unknown variable and so many equations. If you want to do the compare, just pick some number. I can say, hey, I can plug in x equal to 0, and then I'm gonna get to this, and then minus 0 plus 4, and then a times 0 square plus 4, and then plus 0. Well, this is going to be 4 equal to 4a, so a equal to 1. So you can see that two way. We have equivalent way to do it. It's up to you. You want to do the one you want, and then you keep going. Well, keep in mind you have two choice 1 and choice 2. So you can continue choice 2 by yourself if you want, but well, sometimes I like choice 1 better, sometimes I like choice 2, but mostly I tend to love choice 2 better, but sometimes comparing coefficient is not a bad choice. All right, let's say that, oh, I have everything is ready here, A, B, and C, so I'm gonna copy this, and then gonna paste it here. So now I can integrate. All right, integrate this thing dx. This is equal to integrate that dx. Well, I already solved a, b, and c. A is 1. A is 1. B is negative. Oh no, B is 1. C is -1. So this is x minus 1. All right, the rest of the work is going to be your integration skill. So you can have integration 1 over x dx. Well, this is easy. And then plus, well, how do you integrate x minus 1 over x square plus 4? I'm going to split that x to x square plus 4 dx, and then minus integrate 1 over x square plus 4. The reason why I do this, because on the second term here, I can do u substitution. On the last term here, I can get to arctan, right? All right, here. Well, I'm gonna just keep it something like that. So I'm gonna do the u substitution first. It will be x over x squared plus 4, but I'm gonna change the x to dx squared plus 4. This is 2x. All right, cancel. And then this thing is going to be integrate 1 over x squared plus 2 squared dx. Well, you already did in the first 5 minutes. I say that if you have integrate 1 over x squared plus a squared dx here, so the answer is going to be 1 over a arctan x over a plus c. This is what we just discussed on the first 5 minutes, right? If you want to prove it, well, you just, again, pull out a square, you're going to get this. If you pull out a square, right, and then this going to be just a, hey, 1 over a square times a, well, 1 second, 1 integrate 1 over x over a square plus 1 dx over a. So you're going to have 1 over a here. That 1 over a here, going to cancel with a square here. So you're going to get 1 over a. And then to integrate that thing, you're going to get arctan x over a plus c. All right. This is from the knowledge before the midterm. And that you're going to have the answer here going to be log absolute x plus 1/2 log absolute x squared plus 4, and then minus 1/2 arctan x over 2 plus c. All right, this is your answer. All right, any questions? Sounds good, everyone? All right, how do you feel about partial fraction? Give the grade in the chat, please, that how confident you are about partial fraction, A, B, C, D, or B plus or something, whatever. How confident you are, just type in the chat, please, before we start a new topic. So hopefully, if you feel like you want more practice, you can look at example 154, 155, 156, and 157. So this is the practice for partial fraction. For example, like 154, you have to do the decomposition like that, right? You know, this, for me, this technique is super easy, man. Everyone, so like that, and you solve for A, B, C, and then you integrate, right? For example, the second one, this is going to be here, what, ax plus b over x squared plus 1 plus c over x minus 1, for example. Well, the third one going to be, hey, ax plus b over x squared plus 1 and cx plus d over x squared plus 2. Well, if this is hard, we can put square here. So you're going to have ex plus f x squared plus 2 squared. For example, like, but this thing, this is the same idea, but it's just terrible in terms of computation because you have so many unknowns, right? And it's going to be terrible when you compare the coefficient, but you know, you have limited time on the exam, so we are not going to ask you something super terrible to compute the coefficient. So that's why just keep it simple like that. All right, you can practice this 4 question. This is the easy one. All right, let's look at the chat. B, A plus B, A, okay, B, B, C. F for fantastic, B, 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 B. Oh, okay, F plus. How the 2 methods from the previous slide different? Well, they're not the different. You know, they give you the same solution, but this is just the different methods. Well, because sometimes it is easier to plug in numbers. Sometimes it is easier to just compare coefficient. Or if you feel like, hey, you just prefer to do only one method, just do that one. Well, forget about my words that you have 2 ways. I mean, if you feel like you're more comfortable to do one of them, just do that one. You know, whatever you want, but you just need to solve for A, B, C. That is the key. Sometimes D, E, F, well, it depends on unknown variable you have. All right, sounds good. All right, no more question in the chat. Good. All right, we have about 20 to 20 minutes left, so we're gonna just go to next one, next technique. Well, we're gonna get started with integrate sine and cosine first, and then we're gonna come back next week to catch up on that technique and look at integrate sec and tan after. Panurut. Well, I have a question in the chat that are you teaching Cal 2 or Cal 3? Maybe not, because I hate you. I mean, well, it depends on the assignment. So if they ask me to teach, well, maybe, but it seems like my schedule is packed next semester. Maybe you're gonna learn Cal 2 with someone else. No, not me, because you know, everyone hate me. All right, 6.3. So trigonometric integral. So that's one. That's for next semester. So I don't know yet, but well, we'll see. 6.3 trigonometric integrals. We're gonna do integration with sine cosine here. All right, I'll give you 30-second break for me as well. Well, 6.3 and 6.4, this seems to be the hard one. Well, 6.3 is not that hard, but 6.4 is super tedious. I hate it. Well, let's come back to the overview here. We already done integration by parts, rational function by using partial fraction. So we have 2 things left. Today we're going to start a little bit on trigonometric integrals, and then we're going to come back to this thing, trigonometric integral again on next Monday, and also trigonometric substitution. All right, let's start 6.3. All right, I want you to stay about 20 minutes more, so stay with me, please. It just, well, I know you are tired now because you learn all day, but well, 20 or 25 minutes more, please. All right, so let's look at trigonometric integrals. So the first thing that we're going to learn is we are going to look at how to integrate sine to the m and sine to the and cosine to the m. So the idea is, if you see the integral that contains odd power of sine and cosine x, so what you can do is you can pick u to be sine or cosine, and then everything gonna be cancel out. I mean, something gonna cancel out, and then you can solve for integral easily. For example, let's say you have integrate cosine cube. Oh, let's just observe the technique from this example. So if you see that you have integrate cosine cube, well, the technique is you can pick u to be sine x. Once you pick u to be sine x, well, let's see, I pick u to be sine x. So what I have is I have cosine x here because by the chain rule, and then I'm going to pull out one factor of cosine here, so that cosine cancel out. So I have integrate cosine square left du. But because cosine and sine, we have the relationship between them, which is sine square plus cosine square equal to 1. So I can switch cosine square to 1 minus sine square. And then now I can have integrate 1 minus u square du. That can be easily integrated. Does it make sense? Well, the idea is we're going to pick u equal to sine x, so something cancel, and then we can just switch this thing to integrate of polynomial in terms of u, and that is fine. All right, so that is the way to solve the sine and cosine with odd power. So if you have even positive powers here, you have no choice. As I told you before midterm, if you see sine square, cosine square, you cannot do the u substitution because you will get stuck. The only way that you're gonna solve sine square, cosine square, you need to use identities. And this is going to be your identities that you're gonna use. By using this thing, you're gonna switch your even power to odd power, because you can switch sine square to 1 minus cosine square. It's going to reduce you to odd power here, which is better because you can do the u substitution after. Right? Let's see if you have cosine to the 6th power. Well, you can just do this thing to be cosine square and then cube. And then now you can just change your cosine here to that by using identities. And then after you expand the cubic, so you get that, and you can integrate easily. So I'm going to sum up for you here. To sum up, this is going to be the technique for integrate sine, let's say to the m power x, multiply cosine to the n power x dx. Let's say if you want to integrate that. Oh, this is my technique. When I was a kid like you, this is how I memorized. So you can think of the technique here by just memorize 3 things. So first, let's try to pick u equal to sine x first and hope something cancel. If it works, you're good to go. So the second one, you can try to pick u equal to cosine x. If you pick u equal to cosine x and if it works, you're done. Number 3, you can try, if you try the first one and the second one and both fail, what should we do? So we're going to try using identities. So we're going to convert sine square x to that. And then we're going to convert cosine square to that. Identities. Because the third case gonna show up when you have the even power of cosine and sine together. So you have no choice. That means you have to use identities to reduce it. Does it make sense? So the thing that's going to be your friend to help you to simplify, it's going to be the mother formula for trigonometric function. So sine square x plus cosine square x equal to 1. Super important because this is going to be the thing that you use to simplify. So if you memorize the thing that I just wrote here, you can do any question about sine cosine. I guarantee it. Because, well, when I was a kid like you, as I told you, I just memorize this thing and it works all the time. You don't need anything else. Well, it is ridiculous that you would just memorize. Hey, when I have odd power, you just pick this. Even odd power, it's just super hard to memorize. You need to save your memory for something else. Well, it's work all the time. You just memorize like this. All right, so let's do it. Well, we're gonna start by integrate sine to the 5th power x dx. Let's look at the technique here. So what we're gonna do first is we're gonna try pick u equal to sine x. Well, let's try pick u equal to sine x and see if it works. So I'm gonna pick, hey, this is sine to the 5th power x, right? If I pick u equal to sine x, so what happened? If I pick, well, let's say if I pick u equal to sine x, I have du equal to cosine x dx. Just do the u substitution. Well, that means dx equal to du over cosine x, right? And I gonna have sine to the 5th power x, change the x to du over cosine x. Not a good one, because when you do that, you see cosine x here that I circle. Can we cancel with sine square, sine to the 5th power? No cancellation, right? No cancellation. This is not a good choice. This is not a good choice. But if you feel like, hey, this is not working, so we're gonna pick u equal to cosine x. Well, if I change this thing to cosine, this thing gonna be negative sine, right? And this thing gonna be negative sine, and this thing gonna be negative sine. Perfect. Because I'm gonna cancel one side, and then I'm gonna have sine to the 4th power here, which I can switch it back to cosine by using identities. So this works. All right, so we got an idea here. So when you do the solution, well, let's do the full solution here. U equal to cosine x. This is by trial and error. So we pick u equal to cosine x. Well, du gonna be differentiate cosine, get negative sine. All right, here I'm gonna have integrate sine to the 5th power x. Well, I change the x to du over negative sine x. All right, just do u substitution. Well, it's gonna be easy compared to, this is a technique you already learned before midterm. That is what I mean by easy. Integrate. Well, I cancel one factor of sine, so I get sine to the 4th power x du. Well, even the term here, this is not cosine x, but we can switch to cosine x, right? Because we know that this is going to be integrate sine square, everything square du. And yes, sine square is 1 minus cosine square x. Well, memorize sine square x plus cosine square x equal to 1. This is your best friend. This is your best friend. Well, this is the mother formula for trigonometric functions. And then because you can swap sine and cosine by just using that identity. And then here you're gonna have, wow, I feel so much better because this is integrate 1 over u square du, right? And you expand it. So 1 minus 2u square plus u to the 4th power du, right? Expand square, and then you're gonna get now integrate it. So integrate 1. So you get u, integrate that, so get 2u cubed over 3, and then plus u to the 5th power over 5 plus c. To sum up, you're gonna have, well, let's clear out the parenthesis first. So it's going to be negative u plus 2u cubed over 3 and then minus u to the 5th power over 5 plus c. All right, to sum up, integrate sine to the 5th power dx. This is going to be negative u is cosine. All right, 2/3 cosine cube x minus 1/5 cosine to the 5th power x plus c. Does it make sense? All right. Good. All right. Next, we're gonna look at, well, I think 2 more examples for today. Well, example 159. So let's look at cosine to the 4th power x dx. Here, I'm gonna do the same thing with the last question. Man, just memorize this. 1, you're gonna take, you will go to cosine x. 2, you're gonna take 2 to cosine x. 3, you're gonna do the identities. If you don't know how to do that, if you feel like number 1 and number 2 do not work, so you can just use number 3, which is identities. Well, we try to avoid using identity because this is the hard one. I mean, we don't want to do that. It's going to be messy, but we try to pick the substitution first and see if it works. So we're gonna say, hey, if I see cosine to the 4th power, so let's say if I pick u equal to sine x, what happened? If I pick u equal to sine x, this is what happened. I pick u equal to sine. So I differentiate sine, get cosine. Wow, that's look okay to me because you have integrate cosine cube x d sine x, right? You can cancel one factor of cosine. However, you have d sine x. Well, your task is you trying to switch cosine to sine. However, because the odd power here, you have no way, right? How could you switch cosine to sine when you have the odd power here? No, you cannot. Because all you know is just cosine square x equal to 1 minus sine square x. You can't. So, no way. So, this will not work. So the second one is, if you try, hey, let's do another one. What if I pick u equal to cos? Well, we get negative sine here. However, how can I cancel that? Once you take a step back and you already spend 20 minutes on the exam trying to figure out these two things, no. It's going to be something else. Well, if you feel like this is the end of the world, so you can say, hey, man, let's try number 3. So number 3 is going to be the one that you use the identities. So for here, I'm gonna do this to be cosine square. So simplify to cosine square first, because your cosine square gonna be the thing that you can reduce to 1 plus cosine 2x over 2 square dx, right? Well, I'm gonna go back 2 slides here. No formula is given on the exam. If you have to do this, just memorize it. Well, you have to. Well, and the formula of sine square and cosine square, this is pretty similar to each other. The difference is just the sign. All right. Now we can just expand that. So, well, I'm going to pull out number 2 first because I hate it. So I have a quarter, right? Pull out 2 square. So I get integrate 1 plus cosine 2x square dx. And this is going to be a quarter time integrate 1 plus 2 times cosine 2x. And then plus cosine square 2x. All right. You can see that this is not the simple one because even you know, well, let's take a step back and look at the term here. You can integrate 1, right? Everyone know how to do it because integrate 1 dx is just x. You can integrate cosine 2x, right? Because integrate cosine 2x, you just do a substitution and you're going to get just pick u equal to 2x and then that would be good. What about cosine 2x? Can we do that? Actually, we can, right? Because cosine to x, well, we're going to use identity one more time. All right. So actually, this question is already solved. So we're going to do a quarter times integrate 1 dx. Well, this is a simple one. Plus 2 integrate cosine 2x dx. And then plus, so integrate cosine square 2x dx. We're going to use identities one more time. This is going to be, well, slowly, it's going to be 1 plus cosine 4x over 2 dx. Well, again, I will repeat it. 1 here, I have integrate 1 dx. 2 cosine x here, I have 2 times integrate cosine dx here. And then cosine square here. You can view this thing as a, you know what, cosine square of something. This is going to be 1 plus cosine 2 of that thing over 2, right? Well, this means cosine of that 2x going to be 1 plus 2 times 2x, which is 4x here, and then over 2. All right, that is good. Well, I'm trying to be slow because this is usually your mistake when we ask you to do the integrate of trigonometric function. Your mistake gonna start from here, and that's why you will not get full credit, because actually you just did it too fast, and then you skip some minor detail here, and then here you're gonna have a quarter. Well, I'm going to start simplify a little bit first before integrate. I'm gonna do 2 integrate cosine 2x. So for here, I'm going to change this to d to x over 2 so I can integrate easily. Well, you can see number 2 cancel now. And then plus a quarter, 1/2 integrate 1 plus cosine 4x dx. All right, a lot of parentheses here, but let's integrate now. So a quarter, integrate 1 dx, you get x. Integrate cosine 2x d2x, so you get sine 2x, right? Because dip sine, you get cosine. And then plus 1/2. Well, integrate 1, you get x. Integrate cosine 4x, you get sine 4x over 4. Right? And then plus c. All right, I already integrate everything, so plus c. Well, you can leave your answer here if you do not want to simplify. This is good for full credit. But if you want to simplify, so you can. Gonna go slow here. 1 over 4 times x plus 1 over 4 times sine 2x plus 1 over 8 x, and then plus 1 over 6 4 times 4 1632 sine 4x plus c. All right, either way it works, but this is how we integrate this question. All right, any questions in the chat, please? All right, hopefully this is not too hard for you. Did I do something wrong? Oh no. Oh, I can, well, someone gonna say, why don't you just group 1 over 4x and 1 over x together? You can group it together. It's going to be 3 over x, 3 over 8x. So you can. So it's going to be 3 over 8x plus 1 over 4 sine 2x plus 1 over 32 sine 4x plus c. Sorry, I ran out of space, but that is how you do it. All right, so what we learned from this technique is the odd power is easy, the even power is hard. So when you open the exam and then you see the odd power, sweet, this is easy, because one you pick u to be sine or cosine, another one gonna be, or you can cancel something. But if you see the even power here, hey, the nightmare is coming. So you just use identity and just switch it. Let's say, well, you know, if you are asked to do like cosine to the 6th power, you can see that you can do the same technique, and at the end you're gonna have so many terms here. You have to reduce more. You have to do use substitution more. Even just if you climb up to cosine to the 8th power, it's just getting terrible. So the even power of sine and cosine is super hard. It's just getting messy, you know, getting messier. But the odd power one, this is easy to integrate. We're gonna do the last example for today, which is this one, 160, and then we're gonna come back to tan and secant on Monday. All right, let's do this one. Well, after I see this example, just look at the question. I see cosine to the 5th power. Man, I feel happy. So happy that I see the 5th power here, because I expect that if I do u equal to sine or cosine, it's going to work. So let's do u equal to sine first. All right. Let's do u equal to sine. So I'm going to have, well, this is super easy one. All right. So I'm going to change this thing to sine. Right? That means I differentiate sine, get cosine. Perfect. Something cancel. All right. So I'm going to have integrate cosine to the 4th power x square root sine x d sine x. Sounds good. And then now, well, if you feel like this is too hard to see, you can pick u equal to sine x. Well, this is going to be integrate cosine to the 4th power x over square root u du. All right. Your task is you're trying to switch cosine to the 4th power to something in terms of u. That's a piece of cake, because it is going to be cosine square x square and then square root u du, right? Not hard at all. And then now we can, yeah, this is going to be integrate 1 minus u. Yeah, okay. I'm going to do slowly. So 1 minus sine square x square over square root u du. All right, this is integrate 1 minus u square square root u du. All right, this is going to be expand that 1 minus 2u square plus u to the 4th power over square root u. Over square root u, this is going to be u to the negative 1/2, right? Because u square root u, this is u to the 1/2. If I move up to the u to the negative 1/2, so this is going to be that. And then you can multiply it. So you're going to get u to the negative 1/2 minus 2u to the 3 over 2, and then plus u to the 7 over 2 du. All right, and you integrate that. So you have u to the 1/2 over 1/2, right? And then minus 2u to the 5 over 2 over 5 over 2, and then plus u to the 9 over 2 over 9 over 2 plus c. All right, so my answer is going to be integrate cosine to the 5th power x over square root x, sine x dx. Well, simple one. So I'm going to just replace sine there. So it's going to be sine x to the 1/2 over 1/2 minus 2 times sine x to the 5 over 2 over 5 over 2, and then plus sine x to the 9 over 2 over 9 over 2 plus c. To be safe, you don't have to simplify. If you simplify and you get something wrong, you lose your point. But if you feel like, hey, I'm going to stop here because this is the correct answer, well, you can stop. But if you like to simplify, you want to show your skill. I'm expert in simplifying. So I'm going to do, this is going to be 2 times sine 1/2 x minus 4 over 5 sine 5 over 2x, and then plus 2 over 9 sine 9 over 2x plus c. Well, you do not need to simplify, but if you want to, just make sure you have time left. Well, do some other problem first, you know. All right, so this is example 160, and this is at the end of this lecture today. So hopefully you learn some new technique today, and yeah, we're gonna come back on the next Monday. We're gonna learn the new technique, which is the technique of integrate tan and secant together. Well, we're almost there, so we're gonna end chapter 6 next week.